and also the third of the lecture series by Sir Michael on K-theory and index operator, index theory. And the title of his lecture today is Elliptic Boundary Value Problems.
Well, as he explained, this is the third lecture of a series, but I want to make it more or less independent for those who weren't here before. In my first lecture, I talked about the elementary proof. All the lectures are based on old work, but I picked out some things which I think are interesting to say. The first lecture was about the elementary proof of the Periodicity Theorem, which Bott and I gave many years ago, which I'll try to explain, make it clear how very simple it is, basically linear algebra. This proof that we came across, we discovered by accident, so to speak, while we were studying elliptic boundary value problems. So now I want to tell you about elliptic boundary value problems and how this gave rise to the proof of the periodicity theorem and how the proof of the periodicity theorem is needed to study boundary value problems. So we'll start with boundary value problems, then I will remind you later on about the proof of the periodicity theorem. So here is the general story. Elliptic boundary value problems. First of all, if we start off with no boundary, if we have elliptic operators on a closed manifold, then the theory for that, which I'm not going to repeat, you have define what you mean by an elliptic differential operator. With every differential operator, you can construct something called a symbol, and then from that you make a topological construction into vector bundles and K-theory, and then you end up by proving a theorem that tells you how to calculate the index in terms of the symbol, in terms of the geometrical construction that you make from the symbol. So that's the theorem for a closed manifold. And the question is, what happens when you have a manifold with boundary? So if you have a manifold with boundary, then first of all we have to give some definitions. What you mean by elliptic differential operator with boundary conditions, what kind of boundary conditions. And then, as we'll see, the Bott periodicity theorem comes in very naturally in the use of this boundary condition. And then once you've got that, you formulate the index theorem for manifolds with boundary in the same way as for manifolds without boundary. The interesting part is not the proof of the theorem, which is more or less routine, but is in understanding what the boundary conditions are and how they are used. So that's what we have to try and do. But first of all, I'll remind you what we do with a closed manifold, just so we get the constructions going. So if you have a compact manifold, dimension n, and we have two complex vector bundles on the same dimension over x, then we have the spaces of smooth sections of the two bundles, and the linear differential operator is a map from one to the other one, given locally by local coordinates by a k by k matrix of differential operators of some given order R. So when you've got that, then you define the symbol of the operator by looking only at the terms of highest degree R in this case, and then you formally replace the partial derivative operator d by dx by the cotangent vector corresponding to that direction. And so what you get is a polynomial function, matrix polynomial function of the cotangent coordinates at each point, and you do this at every point. So what you get is a function on the cotangent bundle. Sorry, you get that's a bad notation. What do I mean? It's a bad notation. You have bundles E and F are over X. Then you have the cotangent bundle T star of X. You pull up the bundles E and F to the cotangent bundle, and then there you have a map which you call the symbol. So just forget the notation. This is wrong what I've written here. Symbol is a map of the lifted bundles depending on the cotangent vector at that point. The important thing is that the definition of ellipticity of the operator says that this map is an isomorphism away from the zero section of the cotangent bundle. For non-zero vectors, this matrix, which is a polynomial homogeneous of order R in the symbols, doesn't vanish away from the origin. That's the definition of ellipticity. Now, once you've got that, then you can use this symbol to construct a bundle on the over the cotangent bundle of X. But what you do, you construct over the one-point compactification of the cotangent bundle. You have two bundles on a space which are isomorphic far away, then you can identify them far away, and you get a bundle on the one-point compactification. So you could, or equally well, I think of it as an element of the K-theory with compact supports of the cotangent space. So what you construct essentially is an element of the K-theory of compact supports of the cotangent bundle of the manifold. That's what the symbol gives you. I call this the symbol class. And that's what you construct from the definition. And then the index theorem tells you how to calculate that index in terms of that. Now, first of all, just to remind you, the standard examples of elliptic differential operators is that if you have a scalar function, then the standard example is the Laplace operator. And if you have a good example of a vector bundle, is to take the spinor bundle on the manifold, which is spin, and the Dirac operator, which I talked about also in other lectures. And this is another first order system. Here the degree is 1, the other case the degree is 2, the order. And then the index is the difference of the null spaces of the operator and its adjoint. It is called 0 for self-adjoint operators. It's not interesting for the Laplace operator, but it is interesting for things like the Dirac operator, where the adjoint is not the same. And the basic theorem is, of course, that the index is topologically invariant, is unchanged under perturbation. Therefore, it's reasonable to expect to calculate it topologically. And the index theorem gives you a topological formula in terms of the symbol, how it constructed. And just to repeat the construction, so the first thing is you construct this symbol class in the K-theory of, well, I've written it here as the relative K-theory of the unit ball modulo the unit sphere in the cotangent bundle, which is the same thing as the K-theory of compact supports, if you like, of the cotangent space. The second step, having got an element in the K-theory, you can take its Chern classes, Chern character. You get a cohomology class in the cotangent bundle with compact support, and then you multiply that by a certain universal class, which comes from the cohomology of X. You multiply them together, take the highest degree term, and evaluate that on the homology class of highest degree in the ball modulo the boundary, or the cotangent bundle with compact support. And that's formula giving you the index. So this is just to repeat what the index theorem looks like for a closed manifold. So now, what happens for a manifold with boundary? So if you manage a manifold boundary, here's a symbolic picture. This X is the central yellow line, a central red line. The vertical direction is meant to be the cotangent directions, giving you the unit ball. Boundary is the unit sphere. But you notice that the ball bundle over X is itself a manifold, but its boundary has two components. It has, first of all, the component which is the sphere, but then it has a component which is the boundary, the whole ball, over Y, the boundary of X. So I hope that's quite clear. So here, this is X, this is the sphere bundle over X, this is Y, this is the ball bundle over Y, and obviously the boundary of the inside is this piece plus the two end pieces. So now we have an additional part, which is the boundary, the whole ball over Y. So if you had the index problem for a manifold with boundary, and you wanted to construct the symbol class and the index formula, we have to deal with how you deal with the topology and the analysis at the boundary. So now, let me first deal with the topology, which is easiest to define in a way. We have a class for a closed manifold, which is defined in the K-theory of the ball modulo the boundary of X. But now we want to make it, refine it. We want to define it a relative class modulo this part and also the boundary of X relative over Y. Then we would have something similar to what we had before. And so the question is, how do we have to, this is meant to be something which is 0 at infinity, or 0 on the sphere. We want to make it 0 also on here. And what that means is that when you construct the symbol of the operator, X and psi, X being a point, psi being vector, we want to be able to, when X is on the boundary, we want to be able to deform that into the interior of the ball. We want to allow X to go to 0. Of course, if you keep it unchanged, it's a homogeneous polynomial in psi. As psi goes to 0, it will go to 0. we want to deform it in some other way, so it remains invertible. These are invertible matrices away from 0. So on the boundary, we have to think of some way of extending it to the interior, which is invertible. And the obvious extension is not invertible. So this is what you require to give you a topological extension. Then, of course, you could hope to repeat a similar formula. You would take the cohomology class in this modulo is boundary and try to repeat the same formula. So topologically, this is what you would like to do. Now, the very first thing to notice is that this can't be done for a general operator. The fact that even at one point x, this thing you have on the sphere, which is then a matrix, non-singular matrix, the fact that that can be extended to the inside means that that element represents the trivial homotopy class of the sphere into the group. And in general, there are non-trivial classes coming from Bott's periodicity theorem. So it's a constraint. An operator given in general will not have any boundary conditions which will allow this extension. So not every operator will admit an elliptic boundary condition. Now, we leave the topology aside and we come to the analysis. But before we do the analysis, I have to do a little linear algebra. But it's very elementary linear algebra compared with what we've been hearing so far. No quivers, no pathisms, nothing fancy. But you may recognize a few similarities. So we take the ring of polynomials in one variable, C of t, and we look at the matrices over this ring, k by k matrix, because that's what the symbol of the operator will be when we focus on one variable. If you have a matrix, which is a k by k matrix over the ring of polynomials, you can think of this, of course, as a homomorphism of lambda modules between free module of rank k to a free module of rank k, just by putting down the matrix. Now, if you assume that this determinant, this polynomial, the matrix P has a determinant which is a polynomial not identically 0, then it follows that generically this matrix is invertible, or that alternatively that the co-kernel of the map P for modules is a torsion module for the ring of polynomials. Polynomials in one variable have two kinds of modules, free modules and torsion modules. A torsion module is supported at a finite set of points. Free module is over the whole line. So these are free modules, but the co-kernel, if P has determinant non-identity 0, is a torsion module, and its support will be at the zeros of the determinant of P. Now, a torsion module over the ring of polynomials is nothing else than a finite dimensional vector space together with an endomorphism. Because when you have the endomorphism, you define multiplication by the variable t to be the operator, and conversely. So a torsion module is exactly the same as a vector space with a linear transformation to itself. That is, of course, the basis on which one studies linear transformation theory by talking about commutative algebra. Now let us assume that the polynomial pt, which is, we assume it's of degree r, say, in the variable, and let us assume that when you expand the determinant, it has maximal degree, and the maximal degree will be k times r. It's a k by k matrix, the polynomial of degree r, the maximum degree is k times r, and we'll assume that the coefficient of t to the kr is not 0. Okay? That's a simplification, it's not essential. But if you do that, then it's easy to see that the dimension of the vector space M, the module as a vector space, the co-kernel of P, is exactly kr. It's k times r, and if you can get a basis for the vector space by taking the polynomials 1, t squared up to t to the r minus 1, taking their image in M, they give you a basis, and then multiplication by t gives you the linear transformation. And of course the determinant of PT, the matrix, is up to a constant, just the characteristic polynomial of the matrix T. So I told you this would be a linear algebra. Let us assume further that the matrix P of T is non-singular for all real T. In other words, the eigenvalues of the linear transformation are not on the real axis. And because I've included the assumption that the highest coefficient does not vanish, that really means that the point t going to infinity is also not an eigenvalue, not a singularity. So the real axis, including infinity, really is not where the support of M is. M is supported outside the real axis, and therefore the M naturally decomposes this module into two parts: the part where the eigenvalues are in the upper half plane and the eigenvalues are in the lower half plane. And of course you can define the MP plus by using it's the image of the projection operator given by the Cauchy formula, 1 over 2 pi I times the matrix inverse of this transformation here. And that in particular means that if your polynomial P, which is a polynomial in one variable T, if it varies continuously in some other parameter, then this MP will vary, MP plus and MP minus will vary continuously with the other parameter. So if you have another parameter, M of P will be a vector bundle, and M plus and M minus will be two sub-bundles, adding up to the whole space. That's the main sort of construction we need, really. So now let's go to, that was linear algebra. Keep that in mind, we'll come use it in a minute. Now let's return to an elliptic differential operator of order R. The symbol is for each x, you get an invertible R by R matrix away from 0. That will define a symbol class in this pair here. Now, at the point of the boundary, what we do? At the point of the boundary, let's call that little y. Let us choose the inward normal, call that vector nu. I'm going to identify tangent bundle and cotangent bundles. I'm not going to fuss about the difference between normals and conormals. And let eta be a unit tangent vector to y. So I'm going to pick out a particular plane spanned by the normal and one tangent vector. And then you take the vector in that plane, nu plus t times eta, and evaluate the symbol on this vector. So now we will get a polynomial matrix depending on the one variable t. That's what we did the linear algebra for. You fix for the moment the point y, you fix the tangent vector eta at y, and for that you have a polynomial matrix in t. And it's easy to see the assumptions we made about the polynomial matrix, my linear algebra, are going to be satisfied in this case. It's invertible on the real axis because that follows from the ellipticity. This thing. So that will give rise to this vector space M plus, which is the positive part of that module, depending on, of course, on the choice of the parameter eta. As you vary eta around, this is a unit tangent vector to y. As you vary eta around the unit tangent sphere bundle on the boundary, what we will get will be a vector bundle on the boundary. M plus will be a vector bundle on y. Okay, that's so the ellipticity gives you originally gave us a symbol in the inside from which we managed to make a vector bundle on a cotangent bundle of x, which is the ball bundle, which is if x is dimension n, that was a sphere of dimension 2n, the compactification of the ball. Now we, by a different route at the point of the boundary, we make a vector bundle on the unit sphere bundle of y. Now y has dimension n minus 1, so its sphere bundle has dimension n minus 2. The ball itself has dimension, of course, n. The previous case I had a bundle on the sphere of dimension n. Now I get a bundle on the sphere of dimension n minus 2. Okay, you notice the difference in dimension is 2. Now, one little observation. On the sphere, you have, of course, the antipodal map. Every tangent vector, I could take the opposite vector. So I have eta and minus eta. And if you change eta to minus eta in here, it's obviously the same as changing t to minus t. And so that shows you really that m plus and m minus are symmetrical under the antipodal map. In particular, they have the same dimension. So they both have half the dimension of big M. And the dimension of big M was r times k. So at once this tells you that r times k must be an even integer. And either r is even or k is even. In the standard case, for example, well, you could have the Laplace operator, something like a Laplace operator with r equal to 2. If you took k equal to the other case means the rank has to be even, like the Dirac operators have even rank. So now I've just observed that given an elliptic operator, we have two kinds of topological objects we can make. One is defined everywhere in the interior, and essentially a bundle on along the fibers, n-dimensional spheres. The other is defined only on the boundary, and it's defined along the sphere bundle to the boundary, on the boundary sphere, so a sphere of dimension 2 less. And of course, you may remember the Bott periodicity has a connection between these two, which we want to talk about. So now let me tell you what an analyst, how they define what is a good elliptic boundary condition. So if you're an analyst and you study an elliptic operator and you have a boundary condition, you have to consider what kind of elliptic boundary condition will give rise to good problems. A good problem will mean that the boundary value problem we satisfy both the boundary condition and the null space of the operator, gives you, for example, a finite dimensional vector space. And analysts have discovered what are the right conditions. If it's classically, the simplest examples of boundary conditions are to say, for example, the function has fixed value, or value 0 on the boundary, or first derivative is 0, or second. If you have operators of high order, then you may have boundary conditions of large order. And not only that, but you may have a number of different boundary conditions which have different orders. So a boundary condition need not be given by a homogeneous condition. In fact, many examples, it would be natural to have several different orders. So in general, you want to consider on the boundary another vector bundle, G, which is given the decomposition as G1 plus, say, GS. And these other bundles have some smaller dimension, and they have the boundary operator is going to be a map from the sections of the first bundle E to the sections of these different components on the boundary, involving certain number of normal derivatives. And this and the order R refers to the number of normal derivatives. So our symbol now really has each of these BJs has its own symbol, which is defined at a point on the boundary, relative to its own order, and then the whole operator, whole boundary condition, you take them all together, and you have a sequence of such maps of different orders. That would be the kind of boundary operators you would consider. And then you have to define what you mean for this boundary condition to be elliptic. And this is the important definition. So it's defined to be elliptic relative to the given operator D. Given the interior operator, what kind of boundary conditions are you going to allow? And here is what the definition is. Now, for reasons I'll explain, the bundles that appear now are going to be dual to the one we had before, but I'll come to that in a moment. So we take the original map was from the bundle E to the bundle F by this matrix P, the symbol. I now take the dual one going the other way. And this time by change of notation, I'll call M the the co-kernel of that map. This is again all at a pair the nu plus t times eta. So again, functions of this one variable t. So this is what we did to define the module M, except I dualized this. Now the boundary operator went from E into G. So by taking the duals, that will make the dual of G going to the dual of E. And I consider the fiber, just the constant, so to speak, I map it into here because it involves, the matrix involves polynomials. It doesn't go into the fiber, but it goes into the polynomial extension of that fiber. So it goes into the ring, all polynomials. So the boundary condition maps you into here. And now the condition for ellipticity is simply the following, that if you go from here into there, go into there by here, then project onto the plus part, then this composite map should be an isomorphism. Okay? So this is the condition that requires is elliptic if this composite map is an isomorphism. That's what you'll find in books on boundary operators for elliptic boundary value problems. It looks quite complicated, and you understand why you wonder what it means. Why is this a good condition? Well, first of all, just notice a little bit. On dimension grounds, of course, you notice that the dimension G of the total number of boundary conditions has to be equal to the dimension of the space M plus, which we saw already was half the rank times K, and this is the sum of the dimensions of the individual bundles. So you get an arithmetical condition on the dimensions. That's not so difficult. But notice that, for example, if I said, if you took K equals 1, you're dealing with scalars, then you would have, that would be R over 2. You take first order operators like the Dirac, you would get K over 2. Now, second observation is, when we formally, to construct a symbol, we said to replace partial derivative d by dx by variables xi, cotangent vectors. Actually, you should put an I in here, and this is really the Fourier transform. And because it's the Fourier transform, and the Fourier transform is really a duality operation, that explains why the bundles I had above were duals to the one I had at the beginning. So that should explain why we dualize things. Now, the third observation here is that if you look up in the books on partial differential equations, the definition of elliptic boundary condition they give is not quite what I've given here. Because instead of taking the Fourier transform, here I replace all the derivatives by Fourier transform, I get down to polynomial algebra on the boundary. The analysts, they say get rid of all the interior variables, but the boundary variable, the normal direction, they leave it as a derivative. And so they express the answer in terms of an ordinary differential equation for one variable of the boundary. But it's more logical to go all the way and turn that into algebra 2, and that's what the little bit of linear algebra I did was for, but analysts don't like modules and polynomial rings and fancy stuff like that, so they write it out in terms of solutions of ordinary differential equations with exponential functions and so on. But it's the same, it's formally the same, but it's just the Fourier transform of the other one. That's the observation. So I've told you what the definition of ellipticity is, and I've given it to you in an algebraic form. Now I told you before that the interior operator gives you an element of the relative K-theory class of the ball modulo the boundary. And it also gives an isomorphism of the bundle M plus on the sphere with the bundle G, G star is, on Y. Now, let's see. Let me try and say this in words, not following exactly what I've written. With the construction of the operator, symbol of the operator D, there was a bundle in the interior on the n-dimensional sphere and on the boundary on the n-2 dimensional sphere. We know by Bott periodicity that these two things correspond. The bundle on the n sphere and the n-2 sphere are isomorphic in K-theory terms by the Bott periodicity theorem. So if really we could guarantee that the bundle we got on the boundary did correspond to the interior one by Bott periodicity, then on the boundary, the bundle we have, M plus, which varies as you go around the sphere, is identified with the bundle G by the boundary condition. The bundle G does not depend on the vector eta, it just depends on the point Y. So for a fixed Y, it's a fixed vector space. So therefore this bundle on the sphere is trivialized. The bundle, the small bundle, the bundle M plus, is trivialized over the boundary by the boundary condition. If we knew that was really the same by Bott periodicity as the thing in the interior, then it would give us a way of trivializing the symbol of the internal operator along the boundary, which is what we want. Okay? So we see that if you come from this point of view, you find out what the analysts say elliptic boundary condition should be. You see that what it gives you is a way of trivializing this bundle M plus on the boundary. We know with general topological guesswork what we like to do is to trivialize the bundle on the n sphere of the boundary. And Bott periodicity tells us the two things, that the bundles should be correspond. If we can prove that they do correspond by Bott periodicity, then we'll have managed to trivialize the internal bundle on the boundary, and we'll be home. So that's how Bott and I came to realize that these two bundles should be the same. They should correspond by Bott periodicity. And not only should they correspond by Bott periodicity, we should get a definite choice, because just to say that this thing extends and this one is isomorphic to that one, therefore this one extends, that's not good enough. We want to have a definite extension, because different choices of extension would give you different relative elements. So you not only need to have a proof of the periodicity theorem, you need to know the details of the proof in order to carry over the details of the proof to carry out the deformation of your symbol on the boundary. So you need more information than just saying that they correspond. You need to know exactly why, how they correspond. Therefore you need a very detailed proof of the periodicity theorem, which is exactly the proof we ended up with in linear algebra, and which I gave at the beginning. So now, for those of you who were there at the beginning, all you've got to do is to remember what I said. For those of you who weren't, I'll just repeat. So, and the elementary proof of the Bott periodicity theorem, I think this is what I just said now. What we come from linear algebra to say is that, first of all, if you have a polynomial matrix P and you construct this module M plus, that really the polynomial P determines this M plus, but conversely this really determines that because it determines the characteristic polynomial, which gives you another resolution of this module by free modules, and then it's not hard by linear algebra to see the two resolutions are equivalent, namely that the matrix P extended by a lot of ones made stable is equivalent by linear algebra to the characteristic matrix. And this when you have this explicit isomorphism given by linear algebra and by matrices, then you will have an explicit identification of the two bundles, because P directly gives rise to the bundle on the interior, this directly gives bundle on the boundary, and you identify the two, you show how to extend the one to the interior of the boundary, and you prove the periodicity theorem. So you need the proof of the periodicity theorem, you need the exact homotopy that you carry out, and then you carry that out on the boundary, and that is then how you extend it on the boundary. So you see that it's a very elementary, very subtle link between the analysis and the geometry, that the exact analytical conditions you require are exactly the ones that you require for proving Bott periodicity theorem. And if you had come to this in the inverse way, we didn't know if history had been the other way around, and analysts had defined all these things 10 years before, when Bott hadn't done his work, then somebody would have found the Bott periodicity theorem. It would have been called the Smith periodicity theorem, whoever found it. It would have been seen as a kind of corollary of what the analysts required. But fortunately, history was kind to Bott. He got in first, and so it's called the Bott periodicity theorem. And I think very, very correctly, it's perhaps giving too much intelligence to the analysts to think they would have got there by the back door. But it's an interesting fact that the proof you get from analyzing the analytical conditions turned out to be simpler than any other proof we had before. The other proofs are more sophisticated. They are all links between different proofs. But as far as a really elementary direct proof, and a proof which gives you insight, this bit of linear algebra on the boundary is, I think, the nicest way. It's halfway between algebra, geometry, topology, and a bit of analysis. So I find it very satisfying. And I didn't give all the details here, but I gave you the ideas. Those of you who are not been familiar with it can look up the ideas and look at it more carefully. But it is actually a very nice, rather subtle link between the boundary conditions of analysis and the topology and the Bott periodicity. Once you've got the symbol defined, extended, then actually it's not too hard to prove the theorem. You've got now, if you like, once the analysis is given to you, you know that the operator with the boundary condition does define finite dimensional vector space. The adjoint equation is finite dimensional. The index is defined. As before, the index will be topological invariant. On the other hand, we've now constructed a relative symbol in the right place. We apply the same formula as we had in the closed manifold. It makes sense because it's a relative class. We integrate it, and of course we guess that this gives the same answer as before. And once you've seen that, it's not hard to carry out the proof, because in fact these two constructions both have some natural properties, and in particular, you can reduce the problem for a manifold with boundary to the case of closed manifolds by doing two things. First of all, if you have a problem on X with boundary Y, then you can use the manifold Y as a closed manifold. So you can use the index theorem on Y. And that comes about if you have an operator in X with two different choices of boundary conditions, then you find that they differ by an operator on the boundary. And so you can then show that the index of the two different boundary conditions differs by the index of the problem on the boundary, which links the two boundary conditions. Seems very reasonable. That's sort of actually known by analysts in a sense. So that enables you to use the boundary operator Y, which is closed, means that you can vary the boundary condition. All you need to do is for one boundary condition and for the given operator. All the rest follow. So that's how we halve the problem. The other bit, what you can do is you can take the manifold X with boundary, you can take two copies, glue them together, you get a double. Now you get a closed manifold. On this closed manifold, you put your internal operator one side, again on the other side, and calculate the index on the closed manifold. So if you use that operator, and carefully how you patch them together, with the right choice of boundary condition that matches both sides, then you'll get a formula for the showing the dependence on the internal operator, two together, give you the theorem for the general case. So it's not hard. You don't need to do any extra work, really. All you've got to do is to apply this kind of reduction to closed manifolds in a rather obvious way. The difficult part is to find the candidate, find the answer, find the construction, and do it in a natural way, so that when you make all these constructions, everything works out well. And that's why this elementary construction is exactly what you need, makes the proof very straightforward. Well, the references, there's really only one reference. This is more or less the same paper in two different versions. By a paper with Bott, we published, it was a conference in Bombay, in the days when it was still called Bombay. It's now, of course, Mumbai, but the same place. There was a conference in 1964 called The Differential Analysis. I think it was published in Proceedings by the Oxford University Press. And in there, there's a short article by myself explaining this. I think Bott gave a talk, that one, talking about the periodicity theorem, and I gave a talk on the index problem. It's a sketch, but I think enough details are there to construct the proof. And then there's a slightly more formal version of it given in the appendix. There was a seminar run in Princeton on the index theorem in similar period, published by Princeton University Press. One of these, I've forgotten what it's called, but it's one of these orange books. See? What? Edit was Richard Paley, I think, that's right. So there you go. They went through there in all the topology and analysis of the index problem for closed manifolds, and in the appendix I showed essentially what I discussed here. So these are just different variations of the same proof. Here they're a little bit more formal, as suits something produced at the Institute of Princeton, all fancy language. This one was more sort of down to earth, and probably easier to understand. But anyway, that's the reference. So now I think that I've really finished what I wanted to say. So I really left myself 20, even allowing for another 20 minutes of spare time. And I don't think I would want to add much more to that. I wanted to do was to show how the elementary proof of the periodicity theorem really naturally led to the boundary value problem, and conversely how we got to the elementary proof by starting with the boundary value problem. So one tells exactly what happens in the other one, and it's really very, very. I like it. It's very beautiful, very simple, and you learn more. You learn both about the periodicity theorem and about the analysis by looking at it. And you can look at special cases, of course. I could just say, if you take the interesting case for a closed manifold of index problems is the Dirac operator on an even dimensional manifold. By the way, on a closed manifold with a differential operator, the index is always 0 if the manifold is odd dimensional, for reasons of sort of symmetry. The interesting case is even dimensions, like complex algebraic varieties, the Riemann rock, and so on. And the Dirac operator, typically in even dimensions, decomposes into two parts, and one half of it is the operator with an index. If you have an odd dimensional manifold, then there is no differential operator, which is an interesting answer, and that fits in quite well. The example for a manifold with boundary, which would be natural here, would be to take an odd dimensional manifold with an even dimensional boundary, I guess. That's right. And then you would take the Dirac operator in the interior, which actually is formally self-adjoint. So on a closed manifold, we'd have no index, but on a manifold with boundary, we'll have an index, like the Laplace operator has. And then you will connect that up with the odd dimensional manifolds in the interior, even dimensional manifolds on the boundary, and you would link that up with the index of elliptic, the Dirac operator on the boundary. So the interest shifts for closed manifolds to open to manifolds with boundary. It shifts from even dimensions to odd dimensions. Really, the examples actually come that way. But the formal proof you don't need to worry about. You can write it down independently, not knowing. But you notice that in order to have a good elliptic boundary condition, I told you it was necessary that the symbol should extend at one point over the interior. And if you do it in the for the Dirac operator in the even dimensional case, that doesn't work because that's the generator of the Bott periodicity. But if you do it in the odd dimensional case, it does extend. So that fits in. Two things fit together quite nicely. What else can I say? Well, I think it's I don't think I can play it out anymore, really. I mean, I think I said what I wanted to say. I could have gone into more detail, but there wasn't much point in giving you really all the detail that's necessary to get the point across. I think I'll stop. Maybe if you will ask questions about this or about anything beforehand, I'll be happy to answer it. Okay. I mean, you can take advantage of my gap to ask questions about the previous lectures if you like. Since we have time now. Yes, thank you. Right, I could say that. When I talked about boundary conditions, these are classical local boundary conditions. That the boundary condition says you have a function and you specify its value or derivative at a point, which is a local bit of information. But of course, it is possible to consider more complicated conditions, which are global. And this turned out to be necessary in my work with Pedodi and Singer. And in particular, for example, if you take the disk and you study the holomorphic functions, then if you ask for a elliptic boundary value problem just for the Cauchy-Riemann equation, you don't find any because it's just only one-dimensional. But the right conditions are concerned saying that on the boundary, you see, let me put it this way around. For a single operator, we told you the boundary condition should involve half the rank. Right? It goes KR over 2. So if it's scalar and it's half the rank. If the rank is 1, you want half a boundary condition. Well, how can you get half a boundary condition? If the bundle had rank 2, you could take one component. But if rank 1, you can't have half the boundary. But you can globally. If you say the function on the boundary should be the boundary value of a holomorphic function, and it lies in half of the Hilbert space, that is half a condition. But it's global, not local. So there are interesting examples of boundary conditions of that general type. And they, in fact, precisely occur in the even dimensional case for things like the Dirac operator or the D-bar operator, in which the local boundary condition does not work because Bott periodicity tells you it does not exist. So if you want to compute, for example, the signature of a 4-manifold, this is given normally the index of a certain differential operator. That operator its symbol does not extend over the boundary. It does not admit the local boundary condition. So you think it's impossible then to get a theorem about the signature of four manifold which involves manifold with boundary. And it seems to be a pity. So we eventually found a much more subtle theorem which applies to those cases in which you have imposed a global boundary condition. Then it works even for things like the signature operator. And the global boundary condition is always of the same type. It says that on the boundary, your function or your section of the vector bundle has to lie in half of the Hilbert space, half that is the boundary value of like a holomorphic function or a harmonic function. So given by a projection of the half of the eigenvalue of an operator. And this as you can formulate in different ways. One way of doing it, for example, is if you have a manifold with boundary, say this is the boundary, then you think of making this boundary a long tube and a long cylinder going off to infinity. This gives you a non-compact manifold. And now if you say that the function shall be, you're required to be square integrable in L2, and it's a solution of some differential equation, then you find out that on the boundary, in the normal directions, it has to actually involve only half the possible eigenvalues on the boundary, and it has to decay exponentially. Otherwise it would expand exponentially, it would not be in L2. So you don't need to say it lies in half the Hilbert space, you just need to say it extends as a solution, is square integrable, and that's the same thing. So that sounds a little bit more natural in some ways, more nicer. And so that's the one way of formulating the theorem. And now the interesting thing is that, of course, the theorem then has a more difficult. Let's see, I got a little bit of. I have a spare bit of paper to scribble on. I'm not sure I do. Are there any? I don't have any spare. No, I don't have the spare transparent. Unfortunately, this time. Ah, good. Yeah, thank you. Yeah. So, if you have manifold with boundary, x and y. If the manifold was closed, then you would have some index problem, and you would give the answer by some formula, some integral formula over x or something, and that would be index theorem. Now, if we have this global boundary conditions, you have to make a correction term, and you add on something here which depends on y. And what you add on here is not local. It is not given by an integral on y. And what you have to add on here is actually a spectral invariant on y. What happens is that you write your operator d, let's assume that near the boundary, d is something like d by the x in the normal direction plus some operator a on y. So it has a normal derivative and then tangential derivatives. Then this part here is an elliptic operator is on y, and this one operator here may be self-adjoint. But because d by dx is skew-adjoint, this whole lot is not self-adjoint, so this one can have an index. And now operator A is elliptic on boundary, is self-adjoint, it has eigenvalues. And they are, so you can have the eigenvalue lambda, which is discrete, and now you can define, well, like you define the zeta function, sigma lambda to the zeta function will be something like that, summed over all eigenvalues. But here, the eigenvalues are, because this operator is not positive, they can be positive and negative, so you have to take this and multiply it by the sign of lambda. So you take the zeta function of the positive spectrum, the zeta function of the negative spectrum, you subtract them, and then you call this eta function of S, and you leave out the zero eigenvalue if there's a zero eigenvalue. And then you show that this function has an analytic continuation like the Riemann zeta function, and S equals 0 is not a pole, so eta of 0 is defined, and this is the term you have to add in here. So the contribution here is a rather subtle analytical invariant of the spectrum of the boundary. Of course, it's very difficult to compute, but it's naturally defined. what do I want to say? If you take eta s with s equal to 0, that means that you're trying to count the number of eigenvalues. Okay, each eigenvalue counts one. This, of course, includes multiplicities here. This is some of all eigenvalues with multiplicities. If you put s equal to 0, you're trying to count the dimension of the space. So formally, this is like the dimension of the positive spectrum minus the dimension of the negative spectrum. And this formal difference is this quantity here. It's not an integer in general. It's a real number. This is a real number. This is a real number, it's integral. And the difference is an integer. This regularization of dimensions by using the zeta function method is, of course, very familiar with physicists. And this formula is used by physicists in physical situations. This is the nice boundary condition to use. And physicists have used it. It comes in very useful. The one situation where it's very easy to calculate, if y has a involution map at degree 2, which reverses the orientation, these things are so defined that means that this has to be 0, because it becomes the same with one orientation and with the other orientation. This is normally, it all depends on orientation. So if for example, if this was a sphere, then the eta invariant for the standard metric would be the right dimension would be 0. So sometimes it's 0, but usually it's not. And of course it depends. If you vary the metric continuously, this bit varies, this bit varies, and also if you have an eigenvalue here that crosses across 0, then it jumps, and then that will contribute to the integer over here. So in fact, there is a very nice bit of additional fact. If you have here, suppose you take y, and you take y across the interval. So you have, for example, y might be a three-dimensional manifold. Take multiplied. This is okay. You got another beat for me? That's dangerous. Okay. So if we have a manifold y and you multiply by an interval, let's take t be the parameter from 0 to 1. And suppose you have on y, we have an elliptic operator d on y, but depending now on t parameter. So you put on here dt, it goes from t0, d0 to d1. And now, supposing that you can have some isomorphism, supposing that you can glue this end to that end together, so that the operator becomes periodic. Then, in this situation, you have a one-parameter family of operators, dt. These are meant to be self-adjoint, called t. So they have eigenvalues. And the eigenvalues, this is a first-order operator, they can be negative and positive. And as you vary t, they will vary continuously with the parameter t. And sometimes they will cross 0. So one positive one can become a negative one. And so you can count what happens when you go from 0 to 1 over the period. When you get back to the end of the period, the spectrum must be reproduced because you get isomorphism. But what can happen is that there's net gain of positive or negative because, for example, the eigenvalues might be always increasing. And they just all shift by 1 as they go from 0 to 1. They reproduce themselves. So you can talk about the spectral flow. So if anytime you have a one-parameter family of elliptic operators, which is periodic in the parameter, then you have a well-defined integer invariant, which is the spectral flow. It can be negative, it can be positive. It describes the number of times the eigenvalue 0 is crossed as you go from one side to the other. Now, the very beautiful fact is that this is also the same as another integer, namely you take the operator d by dt on y, and you add d by dt on x, and you regard this as an operator on the whole manifold. Now you introduce one more dimension, and this operator now is no longer self-adjoint, because d by dt is skew-adjoint. This operator has an index, and the answer is that this spectral flow there is equal to the index of this one. So the index in this dimension is related to the spectral flow in that dimension. And so this might be dimension 4, this might be dimension 3. Physical space, for example, so space-time. This is a very beautiful fact, and this is related to Bott periodicity in the following way. You remember that the unitary groups have homotopies alternately integers and 0, and the index is related to the ones which are integers, and the other one which is 0. But if you, well, I'll put it down this way. Well, if you consider the space of all Fredholm operators, so the Fredholm operator on the fixed Hilbert space, Fredholm operator is one which is bounded and has a finite dimensional null space and finite dimensional null space for the adjoint, and then therefore in particular has an index. The space of Fredholm operators, called curly F of the Hilbert space, has components given by the integers, the index. And not only that, it has a second homotopy group, is also integers. This is actually a model for K-theory. The maps of X into his space are parameterized K-theory. But now if you look at the skew adjoint, so these are the kind of things I've been talking about here. Then you find a space which I'll call F1. And this space, well, essentially, I'll cheat a little bit, this space turns out to have a fundamental group equal to the integers. Namely, if you take a closed path in this space, it has an integer corresponding to it, just like the unitary group. And in fact, this space F1 is topologically equivalent to the infinite unitary group. So the Bott periodicity theorem about these two spaces, this one and this one. Here you have an integer invariant corresponding to the components, which is just a single operator, index. This one you have to go to one parameter family to see the corresponding thing. But they correspond by Bott periodicity. This is another statement, if you like, of Bott periodicity in a different guise. If you take a 2-parameter family, then you'll get an invariant in here. And a 3-parameter family, a variant in there, and so on. Alternatively, one and the other one. So, but this spectral flow is a rather nice, and this actually has a physical interpretation. If you think of particles and antiparticles, then, and you think of operator like a Dirac operator, it has positive and negative energies, particles, and as they, if you think of some background potential which varies periodically, which may sort of pumped into the system, what this could be interpreted as doing is it turns particles into antiparticles. This number is what you get by the spectral flow. So it has a kind of physical interpretation which is known to physicists. So this is a nice, this is of course closely related to the, this and this are closely related. I didn't, but this is a rather independent statement, but the two things are closely related. So manifold of boundary, you have in addition to these local boundary conditions, this much subtler global boundary condition, which, thank you for asking about, to give me something to talk about 15 minutes. I didn't plan to do that. It's much harder, and it involves much subtler formulas, but it really has a lot of beautiful content, because this you see, is a topological invariant integer discrete. This is a differential geometrical invariant like integral curvature. And this is a spectral invariant involving Eigen Values. And in some situations, applying to rather nice spaces, this actually is related to number theory. Well, I mentioned the eta invariant. It's not the Riemann zeta function, but this is it's related to number theory. If you take I think I can say a little bit in another piece. Another very nice example of this thing with manifold boundary is you take the following. If you take a circle, and here then you take a two-dimensional torus. Sorry, everything looks like a circle, but there's a torus and here is a circle. And you make this here a bundle. This is a three-dimensional manifold Y. And you get it by taking the following. Take an automorphism of the torus. An automorphism of the torus can be given by an element of SL2Z. That mixes up the generators. And once you have an element in there, it's a linear automorphism, you can use that to glue the two tori together. And so for every A, you'll get a 3-manifold corresponding to it. This 3-manifold, then you can put on a natural metric coming from the geometry of this construction, and then you can construct an invariant, this invariant eta 0 of y. So this number, which usually you can't calculate at all, is a complicated number depending on the spectrum. Here, because it's got a concrete example involving the spectrum, you can use the spectrum of the torus, the lattice, and automorphism. You get into number theory because you get the action of this element A in SL2Z on the integer lattice. And in particular, if you take here a hyperbolic element, then the integer lattice is acted on. The points fall into hyperbolic orbits. These are things, elements of the same norm in a real quadratic field. And this number here, which is what we get for the index theory of manifolds of boundary, this turns out we identify to actually the value of essentially a zeta function type for a number field. You write down the classical kind of formulas, and then you value it at 0, and you find the same. So this thing here actually is, in this case, a sort of zeta-type function of number theory, and you get a very nice formula. And this is true not only for the two-dimensional torus, but also for the analogous thing with multi-dimensional torus. It's more complicated. This is rather related to quadratic fields. The other one related, the real quadratic fields. The other one related to real number fields of higher rank. And the same thing works in all dimensions. It's a very beautiful link between. So there you get a link between number theory and differential geometry and topology, and that's the one I like best. Okay, I think I've used up the time. Now, you can ask more questions, but the other questions must be shorter. Would anybody like to ask a question which will require a short answer? Why didn't I put an I? Yeah, but then it wouldn't be interesting. No, the reason is, in interesting examples, if you take something like a Dirac operator, that's what you get. So for the Dirac operators, you find exactly like this, that the one part is, so for on an even dimensional manifold linked with odd dimensions, one half is skew adjoint, the other is so it fits with the example. No, of course I could put an I, but then you don't get anything. There's not an interesting theorem or examples. The interesting ones are of this kind, and it fits in very nicely here. Yeah.